Our textbook is Fundamentals of Electric Circuits, 7th edition. Okay, so in today's lecture, as I said, we'll talk about some of the concepts, including the voltage and the current. We will introduce the definition of the circuit itself and what does it mean. And we will talk about different sources that we will be seeing in our circuits, including dependent and independent sources of current and voltage type. I will provide the link for the bookstore later on course link, so you can buy the textbook. So what is the circuit? A circuit is made of wires that are connecting components together. So part of those components, we have the passive and we have active components, as we'll see later on. Some of those passive components that you have seen in Physics 1010, including the resistors, capacitors, inductors, and in this course we will introduce the operational amplifiers as well. So as you can see here, we have resistors, those are passive components with the light bulbs. We have some measuring instruments here, the ammeters that measures the current. The ammeter has to be part of the circuit in order to measure the current. We have the batteries, and this is a switch. So we will come later on to a demonstration where we show the circuits and some of the elements using one of the softwares that are available in addition to the Tinkercad that you will be using in the lab. This is a simpler software available from Colorado University. The units that we will be using are from International Systems of Units, SI for as a short cut. Some of the units that we will be seeing a lot, including the kilo, micro when it comes to the charges and the capacitances, nano, pico, femto. So those ones are, as you can see here, the multiplier for the micro, for example, is 10 to the power minus 6. You have the mega, which is 10 to the power 6. You have the giga, which is 10 to the power 9, kilo. So those are some of the units that you will be seeing in this course. The first quantity we would like to talk about is the charge. The SI unit for the charge is coulombs, as you've seen earlier in earlier physics courses. The charge of one single electron or proton in magnitude is 1.602 10 to the power minus 19 coulomb. This is the smallest charge that we will be dealing with in this course. So if you want to look at how many electrons, for example, in one coulomb as a charge, then you divide one coulomb with 1.602 10 to the power minus 19, and this is going to be the number of the charges in one coulomb, either as negative charges or positive charges. You've seen such charges, unfortunately not in real labs due to the pandemic, but in our labs that we have introduced recently in 1010 or in other virtual labs. picocoulomb, nanocoulomb, microcoulomb. So as a conservation of energy, those charges cannot be created or destroyed. They can only be transferred from one form to another. So the second quantity is the current. Current defines uh, the conditions of those charges. So if you have a static charges, you don't have a current. Once those charges start to move, then you do have a current. In this case, we can define the current as the time rate of the charges flow. You can look at this current as exactly, and those charges as for example, a water flow. And then as long as this water is flowing, then you do have a current. And the same analogy here is applied for the charges. You can look at those charges. As long as those charges are moving, then you do have a current. Now we have two ways to describe the motion of the charges. Either we look at the electrons, and then we say the flow of the electrons. And in this case, if you look here in this circuit, you will see that the flow of the electron is going in this direction. The convention that we'll be using in this course basically defines the flow of the positive charges. So if you have a negative charge moving from right to left, this means that you have an equivalent positive moving from left to right. And that's why we will say that our convention here that defines the positive direction of the current is the one that is opposite to the electrons flow. So if electrons are flowing from left to right, then my positive current is flowing from, sorry, if the electrons are flowing from right to left, then the positive direction of the current, based on this convention, is going from left to right. So in this case, this is my positive current, not this, right? This is the direction of the electrons flow. For me, I will adopt the convention that says that the positive direction of the current is in the opposite direction of the electrons flow. That's correct. We're using the convention, which is basically the opposite to the direction of the electrons flow.
So, sir.
So mathematically, we can say that the current I is dq divided by dt. And the unit for the current is ampere, which is a coulomb per second. And remember, as long as you have charges that are moving, you do have a current. If the charges are not moving, you don't have a current. What are the two types of signals that we'll be dealing with? We have a DC and an AC. What does a DC and AC mean? DC is a direct current. In this case, we have charges that are moving or a current that is going only in one direction. And in this case, you will see that the current here is constant. The flow is constant. The current is constant. However, the AC, you have charges that are moving in a way such that there is a current, but they are not going in one direction. And this is what we call the AC, which is an alternating current. And this is due to the sinusoidal variation of the charges versus time. So we can look at here. This is the AC signal, and you can see that the current is varying, which means that the charges are going in a way such that it changes, does not go in one direction. Those charges are going in a sinusoidal shape where they increase in one direction and then they flip back again in the other direction, but you do have a motion. The charges are moving, however, they're not going in one direction, and that's why we have an AC signal. Okay, so if we say that the current, my positive current, is going in this direction here. This is my positive current. That is 5 ampere. In this circuit, we're dealing with bidirections. So either the current is going in this direction or going in the opposite direction. We have no other choices. So if I, for example, assume or I know that the current is flowing in this direction with a quantity of 5 ampere. This means if I am to describe this current with respect to the other direction, how can I describe this current? Since my reference for positive is this, then definitely if I am to describe the current going in the opposite direction, I should be calling it minus 5 ampere. Based on my reference here, I know that the current going in this direction is 5 ampere. Then if I am to describe this current pointing in the other direction than my reference here, then I should be saying that this current is right now based on this direction as minus 5 ampere. So this is my reference. That's my reference. Remember, the current is going to go either in this direction or in the opposite direction. Based on which direction your current is positive, if you are to describe it in the opposite direction, then you have to say it's negative. Any questions so far?
Sure. So could we take this to mean current is a vector?
I can't hear you. Your voice is so.
Oh, sorry. So current is a vector then, technically.
The current here has only two directions, either going to the left in one direction or in the opposite direction. It's not a vector in the definition of the vector field that you have seen earlier in physics 1010, where a vector field is basically defined by a direction. For example, like the electric field. Here, it is a scalar based on the direction of the current flow. It does not have other than those two quantities, either, for example, in this way or in the opposite way. Okay? Does this answer your question?
Yes, thank you.
Okay. So let's now look at the voltage. The voltage is the quantity that basically creates the force that pushes those charges to flow in the circuit. As long as you do have a potential difference defined by this voltage difference, let's say that this voltage is created by a battery, and you do have the conditions all met, which means that you do have a closed circuit, that your charges now can flow in that circuit. The one that is responsible for pushing those charges to go into that circuit is the voltage. The voltage is the one that pushes the charges to flow in that circuit. The unit for the voltage is volts, which is defined also by joules per coulomb. So the voltage is the energy needed to push a charge to go between two terminals. So 1 volt is an energy of 1 joule that is needed to move a charge of 1 coulomb between two terminals, between 2 points. And now this takes us to the power and the energy, because the power is related to the voltage and related to the current as well. The power is the voltage times the current. The unit of the power is watts. And also the power is a time rate of the energy. It defines the flow of energy. The power defines how much energy are flowing per time. So the power is also can be looked at joules per second. Now, to discuss the convention of the power that is absorbed or supplied based on the components that we are analyzing, we have to be very careful. We do have components that absorbing energy or power, and we do have components that are supplying energies or power. For example, a battery is a component that supplies energy or a power. A resistor is a component that absorbs energy or a power. Now, the convention that we'll be using to distinguish between which is which one is which is supplying, which one is absorbing, is here, the sign. Just a second. So if we have the current entering the positive terminal, so this is the positive and this is the negative for this component across its terminals. If I have the current enters, which means if this is positive here, I know that the positive is also here and the negative is here. So if this current is entering the positive terminal, leaving the negative terminal, then in this case, the power would be written as positive. In other words, the component that absorbs energy will have its power as positive. So in this case, if you want to look here at this as a resistor, and this resistor has positive and negative here, and the current is flowing this way, then the resistor will have the power being positive. However, if I am to look at this, where the here is the positive and the negative, and in this case, the current is moving from negative to positive. In this case, the power would be negative. And this is, if I am to look here at the battery. So in this case, if this is the battery, and we all know that the battery having the current going in this direction, because the battery is the one that provides this energy and this current. So in this case, if I have the current entering the negative, leaving the positive, then the power would be written as minus VI. So look at always look at it this way. And that's gonna take us later on to the convention. If you want to look at it from the energy point of view, batteries, they do have finite energy. So that's why if you are to charge a battery, for example, right? If you are to charge a battery, and for example, those are one types of the batteries. This is a a lipo battery. So if you can see it here, lipo battery, lithium polymer battery. So this battery, you charge it with a charger, right? And then you use it in whatever application that you are using it in. After using it for some times, you will find that this battery is dead, ran out of energy. Why? Because indeed it is supplying energy to your application, whatever your application is, but it is discharging in that sense. So the stored energy in this battery is being discharged. And in this case, but in our case here, in our course, we will be treating those battery as ideal batteries. So for us, ideal, this means that we're not going to look at the energy stored in those batteries. However, in reality, practically, that's correct. That's correct. So if you hook up this battery to the charger, then this battery now is acting as a component that is absorbing energy. And in this case, it will, although it is storing energy, but if you're looking at absorbing, supplying concept, then yes, you are correct. In this case, if I am, so right now, this battery is discharging, this battery is supplying energy. If I put my battery in the charger, then the current is going to enter into this battery. And in this case, my battery will be charged. If my to be charged, it has to absorb energy. So you can look at exactly it is acting the same way in terms of absorbing energy as the resistor, but they are not dissipating this energy. They're storing that energy inside. So that's the difference. But if you want to look at in terms of charging, discharging, you are correct. The black one here for the battery defines a discharging behavior, and that's why my power is negative in this case, because this battery is supplying energy. But if this battery now reached zero and now I need to charge this battery, this case the current is going to enter in the positive terminal, and in this case the power would be positive because now the battery is absorbing energy. Is that clear? So again, with the conservation of energy, the energy has to be conserved. It does not get created or destroyed. It transforms from one form to another. So if you are to look at any circuit with a scale of energy, you will always have the amount of energy that being supplied equals to the amount of energy that's being absorbed by your components in the circuit. So in this case, you can look at, again, if you recall when we said that the power is the time rate of the energy, which is joules per second, then or watts. So the energy would be here, the watts times the time. Now, if we want to look at the sources that are going to be used in this course, we will be having um, different types of sources. We have voltage sources, current sources, right? Those sources, as we will see later on, will be ideal sources. What does ideal mean? An ideal source for the voltage would be generating a constant voltage regardless of the current. So here, let's start first with the independent sources. The independent sources that we have in this course is a voltage source that defines by a circle with the plus minus defining which one is higher potential than which terminal is higher potential than the other terminal. So in this case, this is an independent source, voltage source, that has this terminal being more positive than this terminal. In other words, the voltage that I see beside this voltage source, this independent voltage source, defines the potential difference between this terminal and this terminal. So I can see this in power supplies, some voltage sources. I can see this in batteries, right? And then I have a second independent source that is also defined by a circle. So all independent sources are being circular in shape. And then there is a small arrow inside defines the direction of the positive flow. So in this case, this is the direction of my positive flow of the current. Now, here for this source, I don't know the amount of current. The amount of current is not constant. The amount of current varies. I don't know how much is this current. This will be defined based on the circuit that I hook up this voltage source to. Here, the current is constant, but I don't know how much of voltage this current source is going to generate. This will be defined based on the components that I am hooking up this current source to. So we talked about our passive components, and we said that only resistors in this course are going to be uh, consuming the power. Capacitors, inductors, as ideal capacitors and inductors, will be storing this energy in those components in different forms. Capacitor will store it electric in electric field. Inductors will store it in a magnetic field. So back to the internal resistance here. If I am to give a real touch to those components and saying that there are non-ideal. If you recall, we talked and we discussed uh, those components being some real component in physics 1010, where at that time we had some uh, internal resistance as um, explaining here for this voltage source, for example. If you recall, we said in voltage source, a non-ideal voltage source will have, if this is a non-ideal voltage source, we said that this is going to be represented with some sort of battery with a small resistance that is connected in series. So this one was the internal resistance for the voltage source, and it is connected in series. Now, in ideal sources, this one will be treated as zero. As an ideal voltage source, the internal resistance would be zero. Now, what about the ideal current source? The ideal current source is represented by this circular shape with an arrow defines that this is a current source. This is a source that generates a constant current. Now, being non-ideal is basically represented as as the following. Now, if you are to compare this with this, you can easily tell that this resistor here that has been omitted basically represents an R of infinity, and that's why it has been removed. So this is an ideal current source, independent current source, and this is a non-ideal independent current source. We will be dealing with ideal sources and discuss. Now, we said that the difference between the current source and the voltage source is basically the amount of voltage. Let's put it this way. Ideal sources, they don't have any restrictions on the maximum power that they generate. In reality, this is not true. In reality, power is extremely important, and it is one of the features that defines the cost of your power supply. So if you look at any power supply that you have, if you look at your mobile power supply, for example, you will see that there's a maximum power that this power supply can handle. In other words, if you try to connect this is this resistance is a part of an internal resistance in the current source itself that is related to the internal dissipation and the heat that gets generated inside that current source. So as I said, ideally we will be treating this resistance as an infinity. I have no internal dissipation. Non-ideal, no, this non-ideal current source has an internal resistance and it has some dissipation inside that you can see it in different forms of dissipated energy. Heat is one of them. Okay, so I was talking about the voltage. Yes, so again, power supplies. One important feature of the power supply is the maximum power that this power supply can provide. If you try to load your power supply, let's say, for example, your mobile charger is one of them, is a voltage source. If you try to load it with higher than the power that this voltage source can handle, you will be, for example, either burning this charger, or if this charger has a protection circuit inside, you will be destroying the fuse inside if it does have. And this again, another feature that you added to the cost of your power supply. So in some, just a second. Okay, so we said that two important features of the power supply of your sources is how much power can this source provide, and if there is a protection circuitry in this power supply or not. So again, ideally, we're not going to look at those ones. We were assuming that our you know source, voltage source, or the current source, or power supply in general, is ideal, which means it has infinite power that can provide us whatever power we want. Practically, this is not correct. You have to be careful and look at the maximum power you can get out of this power supply. Any any other questions? So for the voltage source, we said that the voltage is going to be constant, and the current can take any value based on the circuit that I hooked it up to. For the current source, the current is constant and the voltage can take any value. Okay, any questions so far? Okay. So all what we have here are basically the summary of what we have explained earlier, the difference between the ideal sources and non-ideal sources. Now, let's look at the dependent sources, the other types of sources that we will be dealing with. If you recall, the first type was called independent. And that independent basically generates whatever value it generates, regardless of the status of the other components, based on where you put it in the circuit. The second type of sources that we'll be dealing with are called dependent sources. The difference between the dependent and the independent is the following. The independent sources are circular in shape. However, the plus minus is, and the arrow is the difference between those two sources. So the plus minus means voltage. The arrow defines a direction of the positive current. So here, this is constant. Here, this one is constant. The voltage, the current here can take any value. The voltage here can take any value. The dependent sources are not circular in shape. So this is extremely important, and I want you to pay attention to this. They are diamond in shape. So I have 4 of them. I have 4 of them. Plus minus, which means that this is voltage. What the source is generating is voltage. Plus minus. So I have 2 of them that generates voltage. So what's the difference? The difference here is what is the value that this source depending on. So if I say alpha and V, and I'm calling here alpha as a constant, then this is a voltage controlled voltage source. So this is voltage controlled voltage source. Beta I, this is a current controlled voltage source. So this is a voltage source. And this one is a voltage source as well. But this is a current controlled voltage source. Yeah. Beta I, alpha V. So this one is the one that is controlling how much voltage is generated. Alpha is a constant. Alpha is a constant. We'll talk about it later on. But so far, this is a voltage source and this is a voltage source. Both of them are voltage sources. How did I know? Look at the plus and the minus. However, this one is controlled by a voltage. Because this one is controlled by a current. So this is the controlling the controlling variable, right? That's why we call them dependent. They're different than the independent. The independent generates this voltage, the voltage source, this independent voltage source. It generates this constant voltage regardless of the other values in the circuit. But this voltage source, because it is dependent voltage source, it depends on a second quantity, which is voltage in this case and current in this case. So now I have those two. And as you can see, now because of the error, because of those two little errors, then those are current sources, right? So always keep in mind, if you see plus minus, then this is a voltage source. If you see an arrow, then this is a current source. However, the shape is diamond. This means that this is a dependent source. Diamond that has plus and minus, then this is voltage source. However, it is a dependent one. It depends on I look here. If I see a voltage, then it depends on a voltage. If I see a current, then it depends on a current. Same thing here. So this is a current source. However, it is a voltage controlled VC current source, current controlled. Okay, so we have 4 types of dependent sources. We have 4 types of dependent sources. 2 of them are voltage, and 2 of them, and the remaining 2 are current. One of the voltage depends on a voltage value, and the second one depends on a current value. The remaining 2 dependent current sources, one of them depends on a voltage, and the second one depends on a current. Okay, is this clear? Now, if I look here at this voltage as Vs, for example, then definitely here Vs equals to alpha V, then you can see that alpha is a unitless, right? Alpha is a unitless. Same thing here. If I call this one Is, then Is equals to mu I, then definitely mu is a unitless. If I am here to call this one as Vs, and in this case, Vs equals to beta I, then you can see that the unit for beta is volts per ampere. If you look at this one as Is equals to gamma V, then definitely gamma is ampere per voltage. So you have here alpha is unitless. And by the way, those are just constants. You can name them whatever you want. Sometimes you see them as numbers in the circuit. So those are just to show you the dependence relationship between that quantity that is controlling the source and the total amount of voltage or current generated by those sources.
So,
Is
sir,
this clear?
so the top 2 sources are independent, but the
That's correct. Can you raise up your voice? Your voice is very
oh, sorry. So the top 2 are the independent sources. The four bottom ones are dependent. And this is the convention for distinguishing.
The top two are independent sources. That is correct. The bottom four are dependent sources. And those dependent sources, they cover all the variations of the cases that we have. Voltage controlled by a voltage, voltage controlled by a current, current controlled by a voltage, and current controlled by a current. Does it make sense?
Yes, thank you.
Okay, you're welcome. Okay, so as I said, those four sources that we have, they are from the dependent type sources, and they are ideal as well. So let's look at an example here to see where does this dependence come from. For example, if I have this circuit, and as you can see here, what do I have here? What kind of source is this? I see a diamond, then this is a dependent source. I see plus minus, then this is a voltage source. I see a diamond, then this is a dependent source. I see plus minus, then this is a voltage source. Voltage source means it generates voltage. This is one of the common mistakes that students do in exams. One of the common mistakes. Be careful. Be careful. Understand what kind of sources that you have in your circuit. Diamond shape means dependent source. Plus minus means a voltage source. Now, this voltage source is controlled by what? What is the quantity that is controlling this voltage source? It is controlled by a current. Exactly. So keep this in mind. Distinguish between those two. You see a diamond plus minus, this is a voltage source, dependent voltage source. You see a current, this means it is controlled by a current source. So this is current controlled voltage source. Current controlled voltage source. Controlled by I. Where is this I? You will see that this I is a current somewhere in the circuit. Look, search for this I. Where is it? Okay, it is in this branch. I see. So this voltage source, this dependent voltage source, look what this voltage source is doing. He generates voltage that is 10 times the current that is flowing in this branch. Whatever the current that is flowing in the C component, this voltage source generates a voltage that is 10 times this current. As simple as this. So there is a relationship. There is an expression that combines the voltage generated by this voltage source that is dependent and the current that is flowing in the C component. Okay? As simple as this. So this is how we look at them when we later on comes to formulating and writing the equations for our circuits. This is how we identify those controlling variable and the generated amount of energy. So keep in mind, always keep in mind, if you see a plus minus, then you are generating a voltage. Voltage generated by the dependent source is 10 times the current flowing this in this branch. So in other words, let's assume, for example, if the current here as 2 ampere. If the current here is 2 ampere in this branch, then the voltage generated across this dependent source is 10 times 2 is 20 volts, just to give you an idea. Here we have no idea about what are those ABC are, just to show you where and how this controlling variable would be in our circuit. Okay? No, they don't. They don't. If you look at this, and this is one of the things also that we will discuss later on, is the definition between the parallel and the series. The voltage source here is not in parallel with the C. No. The voltage source here is in series with the B. This whole branch is in parallel with the C. Make sense? Later on, you will take we can take this as our reference. The word grounded here basically means that you're looking for a reference, and we will come to an example. I will show you how to put a circuit together and what is the definition of the reference. I will show you that in a bit. So let's finish from here, and then we will go there. Yes. Okay. So where do we see those dependent sources? We see those dependent sources in transistors, where basically the models of how you hook up the transistor is going to generate binding relationship between your input and the output, where basically your input is a voltage, your output is a current, or it depends on how you hook up your transistor and the circuit. Now, here we will come to the operation amplifiers later on when it's the time for that. But let me now show you this interesting website. Just a second. Okay, so this website, I'll give you the link to this, from University of Colorado, and it's a very interesting virtual lab, that virtual circuit lab that they put together. So in order to show you a very simple circuit, so first of all, we'll grab a battery, and then we have a resistor here, we have a switch. You can change the orientation, another resistor here. You can change the value. Let's put this one as 20. Notice that the coding, the colors of the resistors are changing to give you the values. And then let's get some light bulbs. Put one here. Put one here. Here we have some ammeters. This is to measure the current through the circuit. So let's get 2 ammeters just to show you how is the current. Okay. Wires to do the wiring. Let's do the wiring. Probably you can build your circuit also the same way while we're doing it here. I'm doing the wiring now. I'm connecting those. This is this this simulator is simpler than Tinkercad. Tinkercad is more advanced than this one, but I found this one interesting to show you some of the visual uh, current flow between, and to give you an idea about how is the current is moving. Okay, so this is my battery. Let me increase the voltage here to 30 volts. Now notice that the current, those two resistors here, 20 and 10, one of them is twice the other one. Now if I close the switch, look what's going to happen. Notice how this light bulb is less intensity than the 10, than the one in the 10 ohm. The one in the 20 ohm, yeah, the one in the 20 ohm, the one in the 20 ohm resistor has less intensity than the one in the 10 ohm resistor, and this is expected. Why? You can look at the flow of the current in this branch and that branch. Look how much is the current in the branch, the one that has the 20 ohm, 1 ampere. Look at the current in the one that has the 10 ohm resistor is 1.5 ampere. So they're all linked together. Okay. So if we try to reduce this resistor to 5 ohm, you will see that the intensity of the light became higher. And notice that the current flowing in the branch that has the 5 ohm is now became twice the current flowing in the branch that has the 20 ohm. So what is the total resistance? What is the total resistance in this branch? The total resistance in this branch is 15, right? Because I have this resistor, 5. So let me call this one R1. The total is 15 ohm. What is the total resistance in this branch? I have R2 equals to 10 and 20 are in series, 30 ohm. So R1 is half R2. R1, the total resistance in branch number 1, is half the total resistance in branch number 2. And that's why we have the current being twice as the current in branch number 2. The voltage is constant across. So I have here, both of them are seeing a constant voltage. That's why the current between branch number 1 and branch number 2 are decoupled, right? But look what's going to happen if I do this. Let me break this. And cut this. If I bring a resistor here, I close this one. and I change this, look, if I change the value of the resistance in this resistor, in this one, if I change the value, what's going to happen to the current here? The current will also going to change. Why is the current going to change? The current is going to change in the second branch because the change in the resistance in the first branch affected the total current withdrawn in, in this resistor, which means the voltage drop across this resistor will also change, which means the voltage drop across those two branches will also change. And if the voltage across those two branches change, this means that the current going in this branch will also change. Any questions so far? Okay, so I guess we'll stop here. Today you have your Lab Zero session at 7 p.m. Not that, but maybe we can talk about the voltage. So, for example, remember when we were talking about the reference and the zero. So here, this is the black probe. If I put it right here, and this is the red probe. If I put it here, I will be measuring the voltage difference between this point and this point. So at the end, everything is with reference to whatever we are measuring, right? Everything is in reference to whatever we are measuring. So if I take this probe and then put it here, then this is going to be my reference. And I take this red and put it here, then I'll be measuring negative. Why? Because this tells me how much is the potential at this point with respect to the black probe. So at the end, everything is in terms of the reference. Look at the voltage here. If I put the black here, black probe here, and the red here, I'll be measuring negative because this point at the red probe is less in potential than the point at the black probe. So this is what I wanted to show you today. And if you have any question, please go ahead and ask.